All right. Okay. Should be going. All right. So when you want to find the zeros of a function, so here I have a function f of x, polynomial, degree is 4. I want to find the zeros. That just means you want to solve f of x equals 0. Okay. This is the same as finding the x-intercepts. So if we have x to the 4th plus 5x cubed plus 6x squared equals 0, we can solve something like this if we can factor this function on the left side. So in this case, we can. Let's factor out the largest common factor we have, which is x squared. Take out x squared, and you have x squared plus 5x plus 6. And now that is a quadratic. And factoring quadratics is something you've got a lot of practice in. So this is going to be x, 2 times 3 is 6, and 2 plus 3 is 5. So x plus 2 and x plus 3. So now, once we've factored it, the reason this is useful when it comes to solving an equation is that each of these factors, so if you have a bunch of things multiplied together equals 0, the only possibility is that one of these things equals 0. So you could have, in this situation, you could have x squared equals 0, which will give us x equals 0. Or we could have x plus 2 equals 0, which would give us x equals -2. Or we could have x plus 3 equals 0, which would give us x equals -3. One of those things has got to be true. That means these are our possible solutions to that equation. So polynomial equations, when it comes to solving polynomial equations and finding zeros of polynomial functions, factoring is your friend. If you can factor, then you can get the solutions. It turns out, not only is factoring a good strategy, but factoring is almost the same as finding the solution. It goes both ways. It's like not only does factoring help you find the solutions, but the solutions tell you what the factors are. So it's like another one of these situations where they're almost the same thing, actually. So we're going to dive into that over the next few seconds. But let's go over and do some graphing. So let's graph this. X squared times x plus 2 times x plus 3. I have something else on here, but let's do that later. X squared times x plus 2 times x plus 3. Okay, so we can see here that this graph is the graph of that polynomial function. This is that 4th degree polynomial. It does indeed pass through the x-axis in those three places, -3, -2, and 0. But the way in which it does that is a little bit different. In both of these cases, the graph just passes straight through. But in this case right here, the graph does not pass through. It touches the x-axis and then turns around. So it turns out the reason for that different behavior right over there, the reason for that different behavior there is because this x is squared. If I were to take away that squared and make it just x, now it still has the same exact solutions, but the way the graph passes through at 0 is the same way it did for the other two, which is just go straight through. What happens if we make it, instead of squared, what happens if we make it cubed? If we make it cubed, then the behavior of the graph right here is actually a lot like the behavior of an x cubed graph, the power function graph. This is just like as if you graphed regular old y equals x cubed. It would look a lot like this, right? Except that's not really the graph of x cubed because it's just part of this bigger graph. But the behavior near that x-intercept is similar to a power function. So that is basically what's going on with these things. And this is called multiplicity. If I take one of these factors, I raise it to a power, then now the x-intercept corresponding with that factor, which in this case would be x equals -2, the behavior of the graph near that x-intercept, when you zoom in on it, looks like a power function. So this looks like a parabola. This looks kind of like an x squared function. It's actually upside down, it's negative, but whatever. The point is that it has a behavior similar to a parabola, where it touches the graph in one spot and then moves around. So this is called multiplicity. And it's basically the power of the factor that corresponds to each x-intercept. That is its multiplicity. So you can think of it as like the number of times that factor shows up in the complete factorization. Because saying something's squared, just like saying it's multiplied by itself, right? So it's like there's two copies of x plus 2 when its multiplicity is 2. So let's go back over here and fill out this little thing here. So here we have the definition of multiplicity. It is the value of whatever power that x minus a number is when you see it in the fully factored format. So the multiplicity is 1, the behavior of the graph at that x-intercept is for it to just pass straight through, like a linear function does. If the multiplicity is 2, and instead of passing straight through, it's going to act like a parabola. It's going to touch it and turn around. Okay. If the multiplicity is 3, it's going to act like a cubic function, where it's going to kind of approach from one side and then from the other like that. So it wouldn't necessarily be going down forever, so I should put an arrow there. But it does have that sort of cubic type appearance. Now, it doesn't matter whether it's above or below. Like this could be coming up from above, and this could be coming down from the top, and then could be down afterwards. But it's the general shape that I'm getting at here. This has a parabola type shape, and this one, it passes through for multiplicity 3. It passes through, but it does slow down and kind of levels off as it touches the x-axis. For degree 4, it looks a lot like a parabola, except it's just a little bit flatter. It kind of comes down, it gets a little bit flatter. And degree 5 is a lot like the x cubed situation, except, again, it's a little bit more sort of angular. The higher multiplicity you get, is just like with the higher degree of a power function, the more sort of angular and sharp those corners become. Not actually sharp, of course. They are still smooth, as I showed you earlier when you zoom in on them. But they do look sort of more like a sharper turn. If it was a road, it'd be a pretty sharp. You have to slow down. So that's multiplicity.